Alright, hello class. Today we're going to have a bit of a respite as far as some of the really complicated things we've been doing. This video shouldn't be that bad. Because what we're doing is we're kind of stepping back to what we know integration to be, which is the area between the x-axis and the function itself. Well, it turns out we can do a little bit more than just that. It doesn't have to be just the area between the curve of f of x and the x-axis. We can find the area between two curves instead. And if you think about it, the x-axis is just a line, right? And so hopefully it doesn't seem like it's too difficult of a leap to realize that we can find the area between two curves. And actually, when I probably mention it to you, it's probably one of those things that you could have figured out if you just thought about it. So given that, I am going to focus a little bit more on the more complicated examples, because we can actually start thinking horizontally instead of vertically when we do this stuff. Okay, so let's just get started. Okay, so as we know, if we just have a function, say f of x, and we want to find the area between this graph and the x-axis, right, between a and b, that area is the definite integral. The definite integral from a to b of f of x dx. Alright, so that gives us just the area here. Now, if I instead want to find maybe the area just between, say, an f of x and let's say a g of x, we'll make it look kind of funky. Okay, what we do, this is our A and this is our B, well, we do what we do with any area. We would take the area between f of x and the x-axis, so this area, which in blue is the definite integral from a to b of f of x dx. And then we subtract away the area here. Okay, so this is the area between G and the x-axis. Okay, and when we subtract that away, what we'll be left with is just this in between them. So if I were to just, let's subtract that. Right, so what we're left with is just here, and I'll make that just in pink. In pink, that area is going to be the larger area that we got from f of x minus the smaller area that we got from g of x. Right? So it really is, you just take the integral of f and you subtract the integral of g. Okay, so to put that in a more compact form, this area here between the curves f of x and g of x right, on the interval a to b is, well, that area is going to be the integral from a to b of f of x minus g of x. All right, And it really is just that, okay? Yeah, I mean, in some Calculus 1 classes, you actually learn this there. The book for this particular class doesn't really do that, I don't think. But it is just that. And in fact, how I think about it is if we're in terms of x, and we'll get into that in just a second, I always think of it as the top function minus the bottom function, dx. Okay, so that's if we're thinking about these things with an integral in terms of x, right? It's always the top guy minus the bottom guy. All right, so let's look at an example or two of this, and then we'll move on to how we can do this in the other direction in terms of y, and it might be your first time seeing something like that. All right, so let's say we want to find the area between y equals x squared and y equals the square root of x from 0 to 1. Okay, so let me write that out. Okay, so we want to find the area between y equals x squared and y equals the square root of x over this interval 0 to 1. So we're basically looking for the area of this shaded region here in purple. Okay, now this is probably one of the most famous examples in calculus. I think every calculus class is legally obligated to do this particular example. And the reason for that is because the square root and x squared kind of act contrary to what you might think between 0 and 1, because between 0 and 1, it's the square root that's greater than the square. All right, so to calculate this area, it is basically just going to be, I'm going to write this again. It's going to be the integral from a to b, the top minus the bottom. All right, so in this case, that will be the integral from 0 to 1, right? And these are x values. That's going to mean something in a bit. Okay, so it'll be 0 to 1 of the top function, which in this case is the square root of x, minus the bottom function, which will be x squared. And there we go. Now we have our integral. All right, so this will be the integral of x to the 1/2 minus x squared. And so we just integrate. It's power rules. So this will be x to the 3/2 times 2/3. Okay, remember, you're always dividing by this, but you can think of it as multiplying by the reciprocal, just to speed things up a little bit. And then this will be 1/3 x cubed. And we'll evaluate this from 0 to 1 using the fundamental theorem of calculus. Well, it will be 2/3 times 1 to the 3/2 minus 1/3 times 1 to the 3rd. Okay, so there's our first piece where we plug in the 1. Then it will be minus 0 when we plug in the 0. Okay, and then this simplifies to just be 2/3 minus 1/3, which is 1/3. So there we go. We have the area of this region here. Now, one thing to note, if we wanted to go to 2, of course I lost some of that based on the graph, but notice past 1, the top changes and the bottom changes. So between 0 and 1, our top is here and our bottom is down here, but then the top becomes our x squared after 1, and our bottom switches. So it's possible that these things may switch on us. So let's clean this up a little bit and do that example. All right, so here I've changed the graph a little bit to be easier to see what's going on. It's not really to scale, but here we have our y equals x squared, our y equals the square root of x, and now we want to find the area between these two guys on this larger interval from 1 to 2. Or, sorry, from 0 to 2. Okay, so the area, okay, well, it's basically going to be this area piece plus this area piece, which I'll call A2. Okay, so that total area will be the two of them added together. All right, so we would actually have to set up two integrals here. The total area will be the area between 0 and 1. Okay, and that will be the top here is the square root of x minus the bottom, which is x squared. Okay, so that's our top minus bottom. And the reason we have to split it up is because in this second piece, the top and the bottom swap. So now it's x squared minus the square root of x for this piece. Okay, because now that is the new top minus the new bottom. Right, because they swap there. So anytime the top and the bottom swap, you will unfortunately have to do two integrals. Okay? So, we already did this one, right? We found that that was 1/3. So I'm not going to do that work again. We're going to focus on this one. And it's essentially the same integrals, but with a different sign, right? We're going to get at 1/3 x cubed minus 2/3 x to the 3/2. But now, and I'm sorry, I totally messed this up. This won't be between 0 and 1, it's between 1 and 2. Okay? So, now, I'll leave that 1/3 alone. And I'm going to plug in the 2, so that'll be 1/3 times 2 cubed minus 2/3 times 2 to the 3/2. Okay, then minus, and we're going to plug in the 1, so we'll get 1/3 minus 2/3. Sorry, I'm kind of cramping things in there, but all right, so we'll get this 1/3. This will be plus 2/3, so 2 cubed is 8, so that will be 8/3. And then this, I have 2/3 times 2 to the 3/2. So what this ends up being is 2 to the 3/2, so that is, well, 2 cubed is 8, so that ends up being the square root of 8, which we can simplify a little bit. And then here, this 1/3 minus 2/3, well, that's a negative 1/3. All right, so we have here 1/3 plus 8/3, that's 9/3, so that'll be 3. Minus, now this I can rewrite as 2 root 2. So this will be 4/3 times root 2. And this will become plus 1/3. So I can either write this as a 3, or I can bring this together with the 1/3 to get us a 2/3, or sorry, not 2/3, 10/3 minus 4/3 root 2. All right, now that, doesn't look very meaningful if we're talking about area. That's the exact answer. So if I plug this in my calculator real quick just to see what the number ends up being, I got that that's about 1.45 if you round, all right, just about. So, so there's, one of the few hiccups that can happen in these things is if you have to split it up. Okay, but it's still, you just take it a step at a time. You take it a chunk at a time, and you should get down to the final answer no problem. Okay, so this example is a good look at some of the other types you'll see. Sometimes they'll just explain the graphs to you, and sometimes they will actually say, all right, let's find the area of this shaded region, and they don't really tell you what the limit should be. Well, the lower limit is definitely going to be 0, okay? The upper limit, though, we need to actually find, because with the graph, it's like, okay, the top, whatever, the bottom, whatever, I see it. The top is going to be cosine. The bottom's going to be sine. We need to find where they intersect. Okay, and to do that, well, we set them equal to one another. So to find where they intersect, and some of you probably already know where that is, and that's fine, but I'm going to go through the process because this will work in no matter what case you're talking about. Okay, we're going to set them equal. So I'm going to take cosine of x and set it equal to sine of x. And some people would already know, oh, I know what angle here would make cosine and sine equal to one another. But if you don't, that's fine. You can divide both sides by cosine and get the new equation that 1 is equal to tangent of x. And then I know that tangent of x is equal to 1 when x is equal to pi over 4. Okay, so this value here is pi over 4. Okay, and then the area, now that I have that value, and like I said, some people would see it right here. That's the angle that makes sine and cosine equal, or it makes tangent equal to 1. So we will set up our integral as going from 0 to pi over 4 of the top minus the bottom. So the top is cosine x. The bottom is sine x. All right. Then we're going to integrate. So the integral of cosine x is negative sine x. The integral of sine x is just cosine x. I'm sorry, did that wrong, didn't I? The integral of cosine x is just sine of x. The integral of sine is a negative sine, so we'll get sine of x plus cosine of x. Sorry about that. Then, now we'll just plug and chug, right? We'll do sine of pi over 4 plus cosine of pi over 4. And this is a great example to show that the second part doesn't always just zero out. Sine of 0 is 0. Okay, but cosine of 0 is 1. Okay, so definitely something to be careful about. Both of these are going to be the square root of 2 over 2. And we'll have the square root of 2 over 2 plus the square root of 2 over 2 minus cosine of 0 is 1. Well, this, if we were to add this together, we would get 2 root 2 over 2. So this ends up just being the square root of 2 minus 1, which if we I throw that into a calculator and see what we get. We get about 0.4-ish. Which, that makes sense. Yeah. Okay. And there we go. All right, now sometimes you won't actually be given a graph. They will just describe, find the area of the region bounded by the curves y equals x squared and y equals 8 minus x squared. And note, they don't give you an interval on x. You just need to figure out what your interval should be. And when we say bounded by these two curves, well, if I graph these two curves, let me try that again. Yeah. Well, the first one is just x squared, so that's not that bad. That's it's this u here. Let me try my best to make it at least look somewhat correct. All right, that's good enough. So there's y equals x squared. Then 8 minus x squared, well, that's going to say up here at 8, do another parabola going downwards. Okay, and what they mean by the area bounded by these two guys is they're talking about any closed area that you can get between these two curves. Okay, so they're talking about this region in here. Okay, they're not talking about any regions out here because that would be just this whole expanse out here, right? So what they say, or what they mean when they say bounded by these two curves, they want you to find the most concise, compact, smallest region that is trapped between the two values. Okay, once we have that, then it's just a matter of finding which is the top. So the top is going to be the 8 minus x squared, and the bottom is going to be x squared. Then we need to find the limits of integration. So the limits we need to find, and we do that by setting these two guys equal to one another and solving for x. Okay, so to solve for x here, I'll just move this x squared over and get 8 is equal to 2x squared. Divide by 2 on both sides to get that 4 is equal to x squared. And so x is plus or minus 2. So that means that this lower limit is negative 2, and this upper limit is going to be positive 2. And from there, it's just integration because we have the integral set up the way we need. It's negative 2 to 2 of, now it's going to be the top, which is this 8 minus x squared, minus the bottom, which is x squared. Okay, and you're going to notice some similar work here compared to what we've previously done. You're going to see that we're going to get an 8 minus a 2x squared, which is exactly what we had here, right? We had the 8 and the 2x. If we were to move this over, we get 8 minus 2x squared. You'll see that a lot, though. That's kind of the pattern that tends to show up. Okay, now there are two ways to go about this. Since this function here is even, I can say that that is going to be 2 times the integral from 0 to 2 of 8 minus 2x squared. And I'm just doing that because that will make the math a little easier. I can just plug in the 0 instead of plugging both of these in and seeing what we get. And that's because the area over here should equal the area over here. The way I graphed it, it maybe doesn't look that way, but that's just because these are symmetric. Okay. All right, so let's give ourselves a little more room here. When we integrate this, I'll leave the 2 outside. We'll have 8x, okay, minus 2/3 x cubed. We're going to evaluate this from 2 to 0. And the nice thing about doing it this way is the 0 just cancels out. So really, by the fundamental theorem of calculus, I'm going to have 2 times 8 times 2 minus 2/3 times 2 cubed. All right, now I'm actually going to do this calculation in a way you might not expect. I have a 2 times 8 times 2, I'm just leaving that alone, minus 2/3, and 2 cubed is 8. Okay, so I'm actually just going to factor the 8 out of this. That might seem weird, but there's a method to my madness somewhat. We'll get a 16 times a 2 minus 2/3, and I did this because this is a lot easier to deal with than to say a 16 minus 16/3. All right, so all we have to do here, and we could have actually factored out the 2. Let me go ahead and do that. Let's factor out the 2. from these things. So we'll get 32 times 1 minus a third. Okay, and that just makes our fraction, the math we have to deal with this fraction, easier to play with. Okay, so that's why I did that. So I have a 32, and this will just be times 2/3. Okay, so 64/3 is our final answer. All right. Okay, so now that is really the 3 types you're going to see. I mean, this is probably the most complicated type of problem you would see, where they don't give you the graph, they don't give you the limits of integration. You have to kind of figure out what the top is going to be, what the bottom is going to be, and then what constitutes as the region you're looking for. All right, on top of all that, we can actually start looking at areas in terms of y. So if I see a definite integral between from c to d of capital F of y dy, well, if you remember, the integral from a to b of little f of x dx, this gave us the area between the curve of f of x and the x-axis. Okay, that's what that integral gave us. What an integral in terms of y gives us, well, this gives us the area between f of y, and in this case the function would be x is equal to f of y, and the y-axis. All right, so if I were to graph this, functions that are x equals some capital F of y, they end up looking more like this. Right, so that would be x is equal to capital F of y. And so the definite integral here from c to d would give us this integral. Or this area, sorry. So the area between the graph and the y-axis. Right? So this, you can almost think of it as if it gives us a sideways area, right? A horizontally oriented area versus here a vertically oriented area. Okay? So, when we start doing the area between curves, okay, instead of talking about top and bottom, it now becomes the difference between left and right. And really it's right and left. Okay, so if we have some, say 2 graphs, say I've got a capital F of x here and a capital, and it shouldn't be x, I'm sorry, that should be y. And here this would be a capital G of y. And this is our C and D. The area between these two, oriented horizontally, okay, it's going to be the definite integral between C and D of capital F of y minus capital G of y dy. In other words, it's going to be the definite integral from c to d of the rightmost function minus the left function. Right? Because this is the rightmost, and this is the leftmost. Okay, so when your integral is in terms of y, that's when you start doing things in terms of which is the leftmost, which is the rightmost, versus the bottom and top that you do when you're talking about integrals oriented in terms of the x, the dx. Okay, so let's start looking at some examples of this case here. All right, so in this example, we are asked to find the area of the region bounded by these curves here, x equals y, x equals 2 minus y squared, and the x-axis. Okay, now here is your basically big flag that's pointing to the fact that you're going to want to do this in terms of y. And that's basically because it's given to you as an x equals a function in y, right? We got it x equals some f of y and x equals some g of y. All right, so let's see if we can go about graphing these. And these, with functions in terms of y, they can be a little tricky to figure out. So y equals x, or x equals y is y equals x. That's basically just this line here. So, you know, no real problems there. There's x equals y. Okay. However, this x equals 2 minus y squared, well, if we put in y equals 0, we get x is equal to 2. So let's say here we have x is equal to 2. Okay, so that's when y is equal to 0. And then if we put in y equals square root of 2, okay, let's say it's here, right? We get 0, or x is equal to 0. Okay, and that's the same if we get negative root 2. Okay, so it turns out that this is actually a parabola, right, but it's sideways. So it turns out that these functions, these x equal things and y functions, they sort of satisfy the same shapes that the y equal functions do. They're just sideways, right? They're oriented sideways. Okay, so we want to find the area of the region bounded by these two curves and the x-axis. So the x-axis, of course, is here. And if I can find the well, there are basically two options. I could be shading this region down here or this region up here. So I'm going to, usually, if you're not told, you assume you're working in the in quadrant 1. Okay, so let me add that, because often you would be given all the information you would need. So I'll say in quadrant 1. Okay, so it won't be this region, mainly because that would give us all this out here. Because remember, we weren't told we're doing anything with the y-axis, so that would start shading everything out here. If we weren't told to include the x-axis, we could include all this. Okay, so now it's just a matter of finding this area here. So what we're going to do is figure out what y value this corresponds with, because we know the y value here is 0. So we're going from 0 to something. All right, and so we do that by setting these two guys equal to 0. So I'm going to take y equals to 2 minus y squared, and I'm going to move this stuff over to the other side so that I have y squared plus y minus 2 is equal to 0. And this may factor, I want factors of negative 2 that sum up to be 1, so it could be 2 and negative 1 would do that. So we get y plus 2 times y minus 1 is equal to 0. So we get that y is equal to 1 or negative 2. So this is 1, right? Negative 2, that would be this intersection down here. All right, so we don't need to bother with the negative 2 because we're going from 0 to 1. So the area is going to be the definite integral from 0 to 1, okay, of, remember we do right minus left. So here's our right side. Our right side is this 2 minus y squared, okay, minus the left side, which in this case is the x equals y. Okay, dy. And then we just integrate this. Okay, and I think some of you might get frustrated when I say we just, but this turns out to be essentially a Cal-1 integral. Okay, so it's really the setup that's the trick here. Once you get it set up, it should just integrate, without much problem. So we'll get 2y minus a third y cubed minus a half y squared, and we'll just integrate this from 0 to 1. Okay, so it'll be 2 minus a third minus a half minus 0. Okay, so I'm going to get all this in terms of sixths. So this is going to be 12 sixths, okay, minus 2 sixths minus 3 sixths. Okay, and what would that be? 7 sixths? Okay, and there we go. That's our area. Okay, so what I want to mention is that if the problem, I definitely did not mean to do that, if the problem you're given is in terms of y to start with, like here, set it up in terms of y. Okay, but there are times where maybe it's given to you in terms of x and you would rather make it in terms of y. So let me show you an example of that. All right, so here's an example where even though the functions are given to me in terms of a y equals things in terms of x, I might actually want to do this one in terms of y. So let me show you why I might want to do that. It comes from the fact that if I were to set this up in terms of an x, right, in terms of bottom and top, so the top minus bottom, notice that the bottom changes. So here's our bottom 1 from 0 to 1, but then we get a new bottom here past 1. So from 0 to 1 we have this, this would be y equals 0 as our bottom, and then we have this y equals x minus 1. So we would have to set up two integrals if we were doing it as bottom to top, or yeah, from bottom to top, right? So this would be two integrals. So it would be the integral from 0 to 1 of the 1/2 x minus 0 in this case. Then it would be plus the integral from 1 to 2 of, now it would be 1/2 x minus this x minus 1 business. Okay, let me, there we go. Which, honestly, these integrals aren't that bad. but we would have to do 2 of them. And, you know, you may get to the point where it may just be too difficult. However, in this case, converting to y would not be a huge deal. And we could calculate the area with a single integral. Okay, so let's talk about that. Because remember, when we are looking at areas in terms of y is talking about right. So here's the right side to left. Okay, and notice the right side and the left side don't change. Okay, and then the lower y value would be 0, and then this upper y value we would need to figure out, but it wouldn't be that hard because here's 2. If we plug 2 into this, either of these functions, we get that this is 1. Okay, so in terms of y, this area is going to be the integral from 0 to 1 of, now we just need to convert these to y's. Well, y equals x minus 1, that is basically x equals y plus 1. So there's our rightmost function, y plus 1. And then here, we just move that 2 over and get 2y is equal to x. And there we go. We've set this area up in terms of a single integral. So if you have a case where it would require 2 or more integrals to find the area, but you see that it would be easy to convert, well, just do it. Okay? So, y plus 1 minus 2y, that will give us 1 minus y dy. Okay, and so then we'll end up with y minus a half y squared just from 0 to 1. Plug and chug, we'll get 1 minus a half minus 0. So we get 1/2 as our area. Okay? All right, so this is one of the examples that we would maybe want to convert to y's and do our integral in terms of y instead. Okay, so here's another example that we would definitely want to convert to y, even though it may not look like it at first. And that's mainly because if we tried to set this up as bottom to top, we'll notice here that the top changes, right? So at first, we get this top, and then we get this top. All right, the bottom doesn't change, but the top does. However, if we reoriented this in terms of left and right, well, the left and right sides actually never change, right? This is always the left side, and this y equals x squared is always the right side. All right, so I'm going to want to convert this into y's. And part of that is because trying to find this split point isn't going to be that easy, whereas I already know that my y's go from 0 to 4, just based on what I see here. Okay, so let's start converting to y's. So for y equals 4x, that just becomes x equals 1/4 y. Okay, and then here, y equals x squared gives me x is equal to plus or minus the square root of y. So then the big question is, which one do we choose? Is this a plus square root y or negative square root y? Well, the answer is, since we are in quadrant 1, that implies that x is positive. Well, if x is positive, that means we have to choose the positive one. Okay, so this limit becomes, or this curve becomes, x is equal to the square root of y. And that should be everything we need. Because to find the area now, it's going to be the integral from 0 to 4 of the right side, so square root y, minus the left side, which is 1/4 y. Notice I'm putting these in brackets just to really drive home the fact that we're doing right minus left. Okay, so this is the integral from 0 to 4 of y to the 1/2 minus 1/4 y. So when we integrate this, we're going to get 2/3 y to the 3/2 minus 1/8 y squared, evaluated from 0 to 4. Okay, now plugging in the 0, thankfully, is just going to give us 0. So this will be 2/3 4 to the 3/2 minus 1/8 4 squared minus 0. Okay, so 4 to the 3/2, that's basically taking the square root of 4 and then cubing it. So the square root of 4 is 2, then you cube it, that's 8. So this is 2/3 times 8 minus, now I have 1/8 times 16. All right, so then we get to, let me say 16/3 minus, now 16 divided by 8 is 2. Okay, so we'll have 16/3 minus 6/3, so we end up with 10/3 at the end. And there we go. Okay, so hopefully that should be enough to get you all rolling on the homework. Once you get it set up, I think the toughest part here is really, in general, being uncomfortable with the y-based integrals. And that's understandable because we tend to deal with everything as a y in terms of x, like y equals some function of x, versus the other way around. But the thing to watch out for is, does your bottom or top change? If the bottom or top changes over your interval, then you probably want to switch to a y. Okay, if it's easy to convert. If it's not easy to convert, then forget about it, But these have all been easy to convert. Typically, if you want to swap over to y's, you would only really do that if it's easy to convert. If it's not easy to convert, then just set up two integrals. That would be the easiest way to go about it. Okay, with that, I will talk to you in the next one. So cheers.